Hello everybody, and welcome to Pioneering Proofs. In this video, I will be deriving the formula for divergence in the Cartesian coordinate system. I will also show you what happens when divergence is integrated over a region in space. So if you took a course in multivariable calculus, you may remember learning the formula for divergence in Cartesian coordinates. As a refresher, the formula for divergence of a vector field, f, is del dot f, and this is equal to partial derivative of the x component of your vector f with respect to x plus the partial derivative of the y component of your vector f with respect to y. In three-dimensional space, this is equal to the same thing except you add another term, which is the partial derivative of the z component of your vector f with respect to z. And for n-dimensional space, you just keep on adding partial derivative terms. But where does this formula come from? To answer this question, we will first derive the formula for divergence in the simplest case of two-dimensional space, and then we will see how the procedure can be generalized to three-dimensional space or higher. Conceptually, divergence at a particular point is the flux around an infinitesimally small surface enclosing the point, divided by the n-dimensional volume of the surface enclosing the point. Now we put volume in quotes because although this is the correct term for three-dimensional space, the correct term for two-dimensional space would be area, and the correct term for dimensions of a space higher than 3 would be hypervolume. We can choose any closed surface around the point to derive a formula for divergence. But for reasons that we will discuss later in this video, we want to choose a surface that forms a shape that can be used as a unit in a grid, which is something that can cover all of space without overlap. For simplicity, we would choose an infinitesimal square as our surface. Now let's visualize the geometry. In our Cartesian space, we have a point located at x0, y0. This point will be at the center of a square with side lengths equal to L. And of course, let's not forget the vector field, which we will call F. Okay, so here's a slightly more detailed diagram of our point and its square enclosure. In this diagram, the light blue arrows, green arrows, purple arrows, and orange arrows represent the unit normal vectors protruding from the top, bottom, left, and right bounds of the square respectively. Now remember, unit normal vectors are of magnitude 1, and they are perpendicular to our surface. We also added coordinates that describe the location of each corner of our square. Additionally, the dark blue arrows represent the vectors in the vector field that are located on the surface of our square. Now notice that for each side of the square, I drew these vectors as the same, or identical. And this is because as the size of this square approaches 0, in this limit, the vectors will approach being identical. So now we will specify a few more variables. We will denote our unit normal vectors as n hat, and they will be equal to the vector 0, 1 for all points on the top of the square, 0, negative 1 for all points on the bottom of the square, negative 1, 0 for all points on the left side of the square, and 1, 0 for all points on the right side of the square. We will also define a term that describes a differential length on our square, which we will call lowercase dl. On the top and bottom of our square, the length differentials will be equal to dx, and on the left and right side of our square, the length differentials will be equal to 2 dy. And lastly, we will use delta L to denote our square boundary, which will be expressed as a set containing our intervals for the top, blue, bottom, green, left, purple, and right, orange bounds. As stated previously, the divergence at a particular point is the local flux around an infinitesimally small surface enclosing our point per area. So if we want to find the divergence at a point x0, y0, then we take the limit as the area of our surface approaches 0 of the flux across our surface divided by the area of the surface. In order for our area to approach 0, the side lengths of length L must approach 0, and the area of our square is just L squared. An integral is just the sum of an infinite number of differentials. And we are summing differentials around our square surface. Thus, we can group this sum into 4 terms. The flux across the top bound of the square divided by the area of the square, the flux across the bottom bound of the square divided by the area of the square, the flux across the left bound of the square divided by the area of the square, and the flux across the right bound divided by the area. For each term, the dot product with the unit normal vectors effectively extracts from the vector field its x or y component, and it also changes the sign of the term depending on which unit vector was involved. So now let's focus on the blue term. In order to evaluate this integral, we're going to use a special trick. Notice that fy is evaluated at y is equal to y naught plus L over 2. This means that it is really a function of x, and we will call this function g1 of x. And we will call the indefinite integral of g1 of x uppercase g1 of x. So now if we want to solve this integral, we obtain the limit as L approaches 0 of 1 over L squared times g1 of x evaluated from x naught minus L over 2 to x naught plus L over 2. So now we will multiply the terms inside of the square brackets by 1 in a special way. We're going to divide by L and multiply by L, as you can see here. Now, if we take the limit as L approaches 0 of g1 of x naught plus L over 2 minus g1 of x naught minus L over 2 over L, then this is the exact same thing as the derivative of g1 of x naught with respect to x naught. Okay, so now this is just lowercase g1 of x naught. If we simplify this expression further, and we substitute fy back in for lowercase g1, then we come to the conclusion that the blue term is equal to the limit as L approaches 0 of fy of x naught, y naught plus L over 2, divided by L. Now our sum looks like this. Now, if we isolate the green term, the procedure for simplifying the integral is the exact same. And so we come to the conclusion that the limit as L approaches 0 of fy of x naught, y naught minus L over 2 over L is equal to the green term. Now let's update our sum. If we add the blue and green terms together, we see a familiar limit that we recognize as the partial derivative of fy of x naught, y naught with respect to y naught. We can do the exact same thing for the purple and orange terms as we did for the blue and green terms. And we receive this limit, which is equal to the partial derivative of fx of x naught, y naught with respect to x naught. And this we recognize as the formula for divergence in 2D Cartesian space. We can derive the formula for divergence in 3D space in a similar way. For divergence in 3 dimensions, we use an infinitesimal cube as our surface instead of an infinitesimal square. And the formula for divergence in 3 dimensions follows the exact same format as the 2-dimensional counterpart, except we just have to bump everything up a dimension. So we aren't going to go through the entire proof for divergence in 3 dimensions because we just follow the same format as we did for 2 dimensions. But trying to solve the double integral for each face of the cube may prove to be a little tricky. So I will walk you through solving for the flux of the top face of the cube by using an extension to my special integration trick that applies to double integrals, triple integrals, quadruple integrals, or pretty much any number of iterations of integrals. So in this slide, the blue term represents the flux across the top surface of our cube divided by the area of the cube. Just like before, we will take the term in the integrand and call it a function g1. And this time it's going to be a function of x and y. And so we will define the integral of g1 over x as capital G1x, and the integral of g1 over y as capital G1y. And so if we sub in g1, then we get then we can solve this integral because we have defined capital G1x as the integral of g1 dx. And so the term in the square brackets, which is uppercase g1x of x naught plus L over 2, comma y, minus g1x of x naught minus L over 2, comma y, is going to be equal to the partial derivative of capital G1x of x naught, comma y naught, over, with respect to x naught multiplied by L. And in the next one, the L's are going to cancel out, and that partial derivative is just going to be equal to g1 of x naught, comma y naught. And so we can do the same exact thing with the integral over y. And we get the limit as L approaches 0 of 1 over L of g1 of x naught y naught. And we can sub back in fz to get the limit as L approaches 0 of fz of x naught, comma y naught, comma z naught plus L over 2, all divided by L. And this will be equal to our blue term. So for our blue term, which is the flux across the top face of our cube, divided by the area of the cube, and we add it to our green term, which is the flux across the bottom surface of our cube, divided by the area of the cube, and we obtain one of the three terms for divergence in Cartesian coordinates in three-dimensional space. So note that if you take opposite sides, so if you add the flux for opposite sides of your surface, then they're going to end up becoming these partial derivative terms. So what about divergence in 4 dimensions or higher? This is possible, and it's the same idea except you just bump everything up to your desired spatial dimension. So in this slide, we will explain the reasoning behind the divergence theorem. So at the beginning of this video, we said that we wanted to choose a differential surface that can form a grid in your n-dimensional space. This is because, for example, if you are in 2-dimensional space and you have differential surfaces in the shape of squares, you can use those squares to cover any region in space. This means that adjacent sides of your squares will have unit normal vectors that point in opposite directions, and by definition, they are also equal. So here's your adjacent square. So by definition, they're also equal. And so, and the adjacent edges share the same points, meaning that they have the same vectors from vector field F lining their edge. So if you integrate divergence over some 2-dimensional object, the sum of dot products for adjacent sides of differential squares will cancel out. So you are left with the flux through the boundary of the object. And there is your divergence theorem. So that's all we have for today, and thank you for watching, and subscribe for more math proofs. See you in the next video.